And our next presenter is Chip Blatchley. And Chip, you have the floor.
Okay, thank you, Cliff. All right, I want to start by acknowledging the diverse group of people who are involved in development of this as an idea. One of whom, unfortunately, is very great that Wally Tyner participated in this, but as I'm sure you know, he passed away a couple weeks ago. So I want to acknowledge his contribution to this project, which is really, really important. Okay, anyway, so this is sort of a conventional wastewater treatment plant. This happens to be the West Lafayette wastewater treatment plant, not far from here. And the job that it serves is like the job of most municipal wastewater treatment plants. It removes or transforms conventional wastewater pollutants and protects downstream water quality, and they do a great job of doing this. So while they do a great job in meeting that mission, there are a couple other opportunities that they don't pursue like most wastewater treatment plants. For example, they really don't pursue recovery of nutrients or water or thermal energy. So the focus of this presentation and the project that we're going to be discussing is recovery of thermal energy. So let me just kind of orient you to this. This panel up here represents a time series over 4 years that illustrates effluent water temperature leaving the facility over a 4-year span. The second panel in the upper right illustrates ambient air temperature for that same period of time, minimum, maximum, and mean temperature. If we take the difference between this water temperature and that air temperature as a mean, that's this graph over here. And that represents a driving force for heat transfer. In the winter, we have the opportunity to collect heat. In the summer, we have the opportunity to cool. And the horizontal green line here represents that kind of reference. Below the line means cooling, above the line means heating. And the amount of heat that we can recover depends not only on that difference in temperature, but also the flow rate, which is typically about 10 million gallons a day from this facility. So if you put all those numbers together using this equation, you can calculate how much heat could be recovered from this facility. So just to put some numbers to this, on the order of 30 megawatts of power in the form of heat could be recovered in winter months, and there's an opportunity for cooling in the summer months. And these things are exactly in phase with the need for either heating or cooling because of the way that the water temperature relative to the air temperature works. So we wanted to explore, well, what does that mean in the context of, let's say, Purdue? So this is real data from the Wade power plant at Purdue. The red line at the top represents the demand for heat from that facility in a 1-week period in early January 2018. And the green line down here, my apologies to those of you who are colorblind, it's this jagged line right here, represents how much heat could have been recovered in that same period of time. And so for perspective, it's on the order of 20–30% of the output of the demand that's placed on the Wade power plant right now. So that is a resource that could be harvested that's not being harvested at West Lafayette. And in the summer, more or less the same story to a somewhat diminished degree holds. The green line represents how much cooling could take place. The blue line represents the cooling demand on the Wade power plant as a history. So from this information, we have identified a resource, and then the question is, what do we do with it? So as a team, we've identified a number of hypotheses and objectives for what we would like to do as a research project. So let me just run through those quickly. The basic idea is that we want to first investigate in more detail the transient nature of this resource. And we'll do that by investigating in, let's say, shorter time scale, how the heat, the recoverable heat in the form of this driving force, the temperature difference, and the flow rate vary at, for example, the West Lafayette wastewater treatment plant. And then how does that pair up with the demand for heating or cooling, as the case may be. We also believe that it's possible to use this heat to promote production, year-round production of fruits and veggies in a horticultural setting, probably at or close to a wastewater treatment plant. And that's relevant because if, in fact, we're able to do that, if you look at where municipal wastewater treatment plants are located in most municipalities, it's typically near locations where people at the lower end of the economic spectrum live. So this then represents potentially an opportunity to provide fresh fruits and veggies for people who are at the low end of the spectrum who often lack access to that kind of food. Next issue is that we want to address the social aspects of this. Will people accept this sort of heat or this resource in any setting? And lastly, we want to evaluate the economic aspects of this. Our plan is to implement a pilot experiment at the West Lafayette wastewater treatment plant and to use the recovered heat or cooling to meet the temperature control needs of their buildings at that facility, and also to support a greenhouse or more than one greenhouse to support this year-round agriculture. All right, so the basic idea is that we want to transform this facility from its traditional requirements or its objectives of protecting downstream water and removing pollutants to adding to that the opportunity to recover resources. Specifically, again, we're focusing on thermal energy, but there's opportunities in these other categories as well. So also just kind of to orient you, this is one mid-sized wastewater treatment plant. There's something like 15,000 of these facilities. Pretty much every municipal area in the United States has one. And beyond that, pretty much any source of waste heat could use more or less the same technology. And I should say this is conventional, off-the-shelf, available right now heat pump technology that we could use tomorrow, or today for that matter. So there's something like 8,000 power plants, 135 refineries, 500 natural gas processing facilities, and all sorts of food processing facilities where this sort of technology could be implemented, and we believe it should be, not only in the United States, but in other countries. So as benefits of this project, we see the opportunity, first of all, for recovery of this heat, which now represents a form of thermal pollution, and to use it in a constructive way, especially to support urban agriculture. It provides an obvious opportunity to reduce the carbon footprint and reduce global greenhouse gas emissions in general. We already have established a partnership between West Lafayette and Purdue to do this. The West Lafayette Wastewater Treatment Plant has already given their blessing. In fact, they want this to happen. And we've also identified a local horticultural organization, the Weathered Plow, who wants to operate the greenhouses to do this. We've connected with a number of municipalities in the area, Chicago, Indianapolis, and Detroit, who also have this interest. And we believe that this project addresses the three kind of proverbial pillars of sustainability: environmental, economic, and social. And not only that, we have the team to do this. So perfect. She just said 0. So thank you.
Thank you, Chip. We have time for a couple questions for Chip Blatchley here. Chip, you got one?
Oops, sorry, I'm supposed to be on the spot here. Yeah.
So, in the idea of utilizing the heat and the water to grow food, as well as the utility of the wastewater plant to remove pollutants, how would you sequence that? I mean, we obviously want to avoid growing food with polluted water.
So we're not actually planning to use the water to grow vegetables in this application at all. The water would never touch the vegetables. What we're planning to do is to implement heat pumps at the facility to extract the heat from the water and use that heat for the purposes that we've described. So there's a disconnect. There's a physical disconnect between the water and the vegetables that would be supported by it, or fruit for that matter.
Most of it's kind of very low grade heat is there, temperature references now. So what will be the efficiency of the prototype that we propose to develop at the West Lafayette?
So Travis, I'm going to take a shot at this, but please correct me if I'm wrong. So my understanding is that conventional heat pump technology typically operates with a so-called coefficient of performance of about 4 or something like that. Is that about right, Travis? Which means for every 1 watt of power you put in, you get 4 watts of heat out. Does that answer your question?
Yeah.
That's sort of, and so again, this is off-the-shelf technology. You can buy it at the store right now, although these would be big heat pumps. But okay, thank you.
We have time for one more quick one.
Okay.
If anyone's got a question. Okay, Chip, thank you.
All right, thanks.